Okay, so in last video we saw series of non-negative terms. That means series where the general term a sub n is greater than 0, okay, for all natural numbers. Now what happens if a sub n can be smaller than 0 for some n, right? What happens here? Well, everything that we just saw in the previous video is not valid, okay? All those tests are not valid anymore, okay? But we can distinguish these two these two series we can distinguish this series in two groups depending on if they're absolutely convergent or not. So what is to be absolute convergent? Well, we say this series, okay, a sub n, is absolutely convergent, right, if the series of the absolute value of the terms of the sequence is convergent, okay? So this sequence is non-negative, right? The terms of this sequence are non-negative. So this is a series of non-negative terms, okay? So if this series is convergent, then this, what we call this series, is absolutely convergent, okay? And so this is the same. Then if a series is absolutely convergent like this, then all the properties that I told you before about the series of non-negative terms that are convergent, the things that you can sum them and multiply them, things like that, they cannot be applied to this kind of series if they're absolutely convergent. But if they're not absolutely convergent, so if this is not true, then these series are called conditionally convergent, okay? So is conditionally convergent if the series of the absolute values is divergent, okay? Conditionally convergent. Now conditionally convergent series are interesting because they converge to a value, but that value can change if we change the order of the terms in the sum, okay? Which is nuts. It's crazy. You're just saying, what did I say, right? Well, I'm going to show to you that this is a result proved by Riemann, okay? Riemann, who is another of the big mathematicians in the 19th century. Well, he proved that if you have a series that's conditionally convergent, which means that it's a series of non-negative terms, or negative and positive terms, whose associated series of absolute terms is not convergent, then you can rearrange terms in that series and get whatever value you want, okay? Any particular value, okay? So for instance, take this series, okay? Sum from n equals 1 to infinity of minus 1 to the n plus 1 over n, okay? So this is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 and so on, okay? So this is an alternating sequence, and we know it's not absolutely convergent, okay? Because the sequence, if you take the absolute value of these terms, you get 1 over n, but we know this is divergent, okay? Because this is the harmonic series, right? So if this is convergent, and we will see it is later, this is conditionally convergent, okay? So I'm going to show that. So let's say this is convergent, so it has one value called s, okay? I'm going to show to you that we can rearrange the values in this sum, and we can get another value of s, okay? So let's see. Let's call it s prime is, and what we're going to do is we take one positive value, and then we're going to take two negative values, okay? Minus 1/2 minus 1/4, okay? And then plus 1/3 minus 1/6 minus 1/8, and then plus 1/5 minus 1/10 minus 1/12, and so on. Okay, so one positive followed by two negatives, and we can do that, okay, because there are infinite terms like this, right? So now we're gonna associate these couples, okay, the first positive with the first negative in its in its couple. So this is 1/2, this is 1/6, this is 1/10, right? So then we have 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus 1/12 plus, and you can see how it goes. This is just 1/2 of this, okay? 1/2 of 1, 1/2 of 1/2, 1/2 of 1/3 is 1/6, 1/2 of 1/4 is 1/8, 1/2 of 1/5 is 1/10, 1/2 of 1/6 is 1/12, and so on and so forth, okay? So the value of this is just 1/2 of s. So we have gotten the value of this sum, which has the same elements as this one, okay? We haven't changed any element. We're just changing the order with which we sum these elements. The result that we get is a different number now, okay? So that's a weird thing, and that's what I was saying. This is a weird thing of real numbers, and in particular infinite sums of real numbers, okay? When you're summing infinite number of things, then things get crazy, right? So be careful about this. When something is conditionally convergent, that means that the series of the absolute terms of the sequence is not convergent. Then weird things happen, okay? So, well, before we end, there's this, a particular case of this kind of series of series that have both positive and negative terms, that can be written like this, okay? Minus 1 to the n times a sub n, or minus 1 to the n plus 1 a sub n, okay? It doesn't matter, okay? It just means that the first term will be negative, okay? And this means that the first term will be positive, okay? Both series are called alternating, okay, series. It's kind of self-explanatory because each term in this series will change sign, okay? There will be minus positive, and this minus plus, just like the one we saw before, okay? Well, there's just one test for alternating series, and it's called Leibniz test. And again, Leibniz was a mathematician in the 17th century, sorry. Okay, just at the time of Newton, and he and Newton were not particularly friends. Okay, so this Leibniz test says that if a sub n is a sequence that decreases monotonically, okay, so it's going like this, and the limit of a sub n is 0, okay, then the alternating series minus 1 to the n plus 1, or it doesn't matter if it's minus 1 to the n of a sub n, okay, so the sum of this, if this is 0, then the sum of these terms that they are getting closer and closer and closer to 0, right? Closer and closer, but each time you have a positive or a negative value, then Leibniz says if these conditions are true, if this sequence decreases monotonically and its limit is 0, then this series is convergent, okay? It doesn't say anything about it being absolutely convergent, okay? So for instance, we can apply this test to this this series, as we have seen, and so Leibniz says this is convergent, okay, but it's not absolutely convergent because the absolute value of this is 1 over n, and the sum associated with this is the harmonic series. But for instance, if you have this minus 1 to n plus 1 over n squared, Leibniz says that this is convergent as well, but it is also absolutely convergent, because the sum of 1 over n squared from n equals 1 to infinity is convergent. Okay, so just remember that the Leibniz test doesn't tell us anything about the absolute convergence of the test, just that if it is conditionally convergent or not. Okay, so that's the end of it.